So, in this last module on mechanics or dynamics of particles or bodies, I would like to say some more about the Kepler problem, namely motion in the 1 over r potential, because of its importance to us both in celestial mechanics as well as in electrostatics, many other parts of physics as well. The 1 over r potential, the Coulomb potential or the Kepler potential, is a very special kind of potential, and it exhibits motion in it exhibits some very weird properties which are not exhibited in general in other central forces either. And this is something which is worth remembering, and that is the reason I would like to spend a little bit of time on this. Before I do that, you recall that the last time we talked about centrifugal and Coriolis forces as non-inertial forces. Now, it is likely that this term non-inertial might give the wrong impression that it somehow has something to do with the lack of inertia. Not at all. In fact, the right terminology for it, for what we call non-inertial forces, should really be called inertial forces, because they arise in an accelerated frame of reference due to the inertia of a body. So, they should, properly speaking, be called inertial forces, or if you like, non-inertial frames of reference have these forces appearing due to the motion, due to the fact that they are accelerated with respect to inertial frames. So, the proper terminology would be inertial forces, but we understand what we mean when we say a pseudo force or a non-inertial force. We mean an inertial force like the Coriolis force or the centrifugal force. All right. That said, let us go back and examine what the motion of a satellite does, how it can be described in two different frames of reference. And there is a common error which is to confuse the two frames, namely the laboratory frame or the terrestrial frame, which is fixed with respect to a point on the surface of the earth, and the frame of reference of a person in an artificial satellite, for instance. The idea is the following: if you want to describe the motion of a satellite going around the earth, for instance, like the moon or an artificial satellite, then from our point of view, from the lab frame, it looks like this. So, from the lab frame or terrestrial frame, here is the center of attraction, and that is the motion of path of the satellite, goes around in some closed orbit. Then, as far as we are concerned, the object here, the satellite of mass m attracted by a body of mass capital M, sees a gravitational force. So, the gravitational force on the satellite due to the earth, due to the attracting body, this is equal to minus g, the mass of the earth or the attracting body, times the mass of the satellite divided by the square of the distance between them radially inwards. And that is a physical force, the gravitational force. And in this force, this object moves in a path which is dictated not only by the force but also by the initial conditions on this body, namely what are the initial velocities and position coordinates like. One should equate this force, one should equate it to the radially inward force of an object moving, for instance, in a circular orbit. This would be equal to the inward centripetal force which from kinematics we know is equal to minus m times v squared over r e sub r. And that part is kinematics. So, this part is dynamics, the thing that tells you that gravity exerts, a mass exerts a force of gravity on all of the masses, that is dynamics, and this portion comes from kinematics. We have already seen that when an object moves in a circular path, for instance, then it has got a centripetal acceleration, and if you multiply it by m, it gives you the centripetal force on the object. And together these two equations will imply, m cancels out, as you can see, it implies that v squared over r is equal to g times capital M over r squared. Okay. So, again, to be very careful, this portion comes from kinematics and it is the centripetal acceleration multiplied by the mass, and this portion comes from dynamics, from Newton's law of gravitation, and together for consistency this condition has to be satisfied. And if it is in a circular orbit, for instance, would imply that the linear velocity is the angular speed multiplied by the radial distance r, and if you put that in, you get omega squared over times r is equal to gm over r squared, or since omega is 2 pi over the time period, it says r cubed over time period squared equal to gm over 4 pi squared. This is Kepler's third law for a circular orbit. Kepler's third law in the special case of a circular orbit of radius r. We know that Kepler's third law is applicable even to elliptic orbits, and we saw last time that a simple scaling argument for the Coulomb potential or Coulomb force tells you why this is so. But this law here arises very simply in this framework for a circular orbit. It is a simple derivation here of Kepler's third law that r cubed is proportional to t squared, which is equivalent to saying that all possible orbits of all possible radii are possible such that the radius and the time period are related by this common ratio. By this ratio is invariant, it is a constant for a given attracting body. Now what does it look like from the point of, well, what is the actual state of motion of this object? It is in free fall. Not only is a satellite, but every point in it, every object in it is in free fall with exactly the same centripetal acceleration, and therefore there is no weight, there is no reaction on a scale. For instance, if an astronaut stood on a scale, that is the reason the astronaut is weightless when in an artificial satellite in free fall. Incidentally, this is exactly the reason why we do not on this earth feel the centrifugal force due to our revolutionary motion around the sun, because it is exactly balanced by the gravitational attraction of the sun from our point of view. But from the sun's point of view, from a frame fixed at the center of the sun, the earth and everything on this earth is in free fall in the gravitational field of the sun, and therefore objects here do not feel that force. We will see this in a different framework in a minute, and that is to look at it from the point of view of somebody sitting in the satellite. So let us say satellite frame. In this satellite frame something very different happens. Here it is a rotating frame of reference, and therefore there is a centrifugal force, an inertial force in this frame of reference, which is experienced by an astronaut sitting in there, in addition to the gravitational force here. So in this case the two forces are F gravitational inwards towards the center of the earth, plus F centrifugal, and this is equal to 0 because they balance each other exactly. This force, if you recall, has magnitude gm over r squared times little m, and it is directed inwards, and if you recall what we derived for the centrifugal force, this was minus m omega squared r, where omega is the angular speed of this rotating frame as seen from the inertial frame. In other words, it is the angular frequency of the orbit, and this is equal to 0, and you will recognize that it is exactly the same equation as in this case. Okay. So from the point of view of a person sitting in the satellite, there are two equal and opposite forces acting on him, not an action-reaction pair by any means. There are two equal and opposite forces acting on him. The inward force due to the Earth's gravitation, and the outward force due to the fact that this is a non-inertial frame and there is a centrifugal force which is tending to fling him out. And these two cancel each other and you get exactly the same equation as before. This of course is the same thing as happens to us when we are on the surface of the earth. We do not feel the gravitational force of the sun while we are on the earth, because we have also an equal and opposite centrifugal force tending to fling us outwards. These two cancel, and therefore as far as we are concerned there is no net force on us due to the sun. All right. So once that is clear, let's go on to the next statement. And this had to do with the scaling relationship, and I need to explain something here. We saw that if you have a central force in which the equation of motion, an attractive central force say, which is of the form minus k over r to the power n e sub r, where n is some index, some number, then we saw that this will imply that if you change the length scale by a lambda, so I put r equal to lambda r prime, and the time scale by some factor mu t prime, then the physics of the situation is unchanged if lambda to the power n plus 1 is equal to mu squared. This came by substituting for r and t in terms of r prime and t prime on both sides, and recognizing that a factor lambda is going to come out from here and lambda to the n here, so the two add up to give you this, and mu squared comes in the denominator here, and you get this condition here. In particular, and these are the two important cases, n equal to 2, that is the Kepler problem. Inverse square law of force will imply that lambda cubed equal to mu squared. This is Kepler's third law. In the following sense, it says that if this force, 1 over r squared force, supports an orbit with a mean radius r, and this orbit has a time scale, a time period t, then it also supports the same potential or force, also supports any other orbit radius r prime, orbit of radius r prime and time period t prime, such that r cubed over t cubed, t squared is equal to r prime cubed over t prime squared. So that's the content of this law. This scaling argument does not prove that the inverse square law potential supports closed orbits in the form of ellipses. It doesn't do that. It only says if it does so, if it supports closed motion with these parameters, mean radius r and time period t, it also supports any other r prime and t prime, such that r over r prime cubed is equal to t over t prime squared. So that's all it says. Okay. In the other case, the other special case was n equal to minus 1. This corresponded to an r going up here and would give you an equation of motion which is d2r over dt2 equal to minus k times r times er, but that's the same as minus k times r. In other words, you have a force which is a restoring force trying to push you back into the origin, proportional to the instantaneous displacement, and this is a harmonic oscillator. This force is a harmonic oscillator in 3 dimensions, not a linear oscillator, but in 3 dimensions. And in this case, there is no relation here. This becomes lambda to the power 0, which says the time scale or time period is independent of the length scale of the motion. In other words, it's not dependent on the amplitude of the motion. This is the property of isochronicity of the simple harmonic motion, namely the time period is independent of the amplitude or the total energy. So that well-known property emerges from this scaling thing here. Now one might get the impression from this argument that somehow for an arbitrary value of n, positive or negative, you have closed orbits. Not true, not true at all. In fact, it's much more rigorous than that. It says, there's a theorem which says, it's got a name, so let me write this down. It's an important theorem. It's called Bertrand's theorem, and it says for bounded motion, namely motion such that the radial distance from the center of attraction doesn't go off to infinity, but we are looking at only that class of motion which is bounded. For bounded motion, the only central potentials leading to closed for any bounded motion, closed orbits are the cases n equal to 2 and n equal to minus 1. In other words, another way of saying it is, every bounded motion under one of these forces, either the harmonic oscillator force or the inverse square law force, leads to a trajectory for the particle in physical space which is a closed orbit. Okay. Whether it's an ellipse or not is a separate question, and the answer is yes, they are ellipses in general, but these are the only two cases in which you have closed orbits. In general, you don't have closed orbits for other values of n. Even if they are central potentials or central forces, you do not have. Bounded motion need not have closed orbits. For instance, you might have bounded motion in some of these forces for different values of n, which look like this. So there's a minimum distance r minimum and a maximum distance r max, and the particle on the body does motion like this in some complicated curve which may go in and out, r may change, never leave this annular region, but it does not close on itself, not a periodic orbit. So that's a very, very crucial point with Bertrand's theorem, which tells you that only these two potentials, for deep technical reasons, these potentials have some deep symmetry properties which we won't go into here, which lead to this beautiful property that all bounded motion in these forces, in these special forces, lead to closed orbits. Okay. The difference between this potential and this potential is that here Kepler's third law says that the time period squared is proportional to the cube of the mean distance from this attraction center, but in this case it says, the same kind of argument says, that the time period is independent of the amplitude of the motion or the linear dimensions of the orbit here. In both cases you have elliptic orbits. In this case, Kepler's first law tells you that the center of attraction is at one of the foci of the ellipse, but in this case Kepler's law tells you, there's no first Kepler's law here, it tells you that the ellipse is at the center, the center of attraction is at the center of the ellipse rather than one of the foci. That said, one can ask what the energy looks like for different classes of orbits in the case of the, or trajectories in the case of the inverse square law potential. Well, here you got to go to, this is an attractive inverse square law force because there's a minus sign here and k is a positive constant here. As you know, if you have a repulsive Coulomb potential or a 1 over r squared force, then you have only open orbits. There's no question of a closed orbit, no capture, just scatters in a hyperbolic orbit. In this case, what happens is that the total energy of the system is the sum of the kinetic energy minus the gravitational potential, minus k over r in these in this notation that I've chosen. K is capital G, capital M, etc., etc. Not bother about it. It's some constant over r squared here for this. This quantity is a constant in the sense that for any given motion, for every orbit, this is some value. This is some constant here. Then what happens is that if E is less than 0, this implies elliptic orbits. Okay. But if E is greater than 0, this implies hyperbolic open trajectories. Different values of E lead to different hyperbolic orbits, but they are not ellipses. They are not it's not captured. It's not bound motion. And you could now ask, what is E equal to 0 correspond to? Exactly equal to 0 correspond to? Everywhere on this trajectory, E remains 0. It's a constant of the motion. What does it correspond to? Not surprisingly, it will correspond to an elliptic orbit in which, if you recall, here is an elliptic orbit with the sun at, or the center of attraction at one of the foci. It will correspond to a case where the other focus goes off to infinity. This moves off to infinity and you get a parabolic orbit. or trajectory. Okay. So this value of the total energy provides you with a way of classifying the kind of motion you have. Either you have unbounded motion in a hyperbola, or you have bounded motion in an ellipse, or the case between the two, the case that separates these two classes of motion, corresponds to E being exactly 0 at all instants of time, and that corresponds to a parabolic trajectory here. Now what else is special about this inverse square law of force? And here is a fact which is very, very significant, which is what makes this potential this force so special. We know that the second law of Kepler, Kepler's second law, which says that the radius vector sweeps equal areas in equal times. So here is the radius vector, it sweeps in some given instant of interval of time, it sweeps that area. Later on it sweeps in the same interval of time, it sweeps an equal area, and so on. We already saw that this is nothing but the conservation of angular momentum. So this is equal to conservation of orbital angular momentum about the center of attraction. In other words, this quantity L equal to r cross p is a constant of the motion, and therefore you can evaluate it at any instant of time. It's going to be exactly the same thing at all points on the orbit. In particular, if you evaluate it at this point, when it's here, r is in this direction, that's the direction of r from O outwards, and if the orbit is described in that sense, p is sitting here. So r cross p, a vector, comes out of the plane of the board. So in this case, the orbital angular momentum comes out of the plane of the board and is constant in magnitude as well as direction. So everywhere on the path, L has exactly the same direction and the same magnitude, no matter where you are. And that's easy to see, because what you have to do is to take dl over dt, this is equal to dr over dt cross p plus r cross dp over dt, but dr over dt is the momentum divided by m. So this is equal to p cross p divided by m, and that is 0 because the angle between p and itself is 0, the sine of that angle is 0, plus r cross the force, because dp over dt by Newton's second law is the force on the particle. But this force is inverse square, so this is equal to r cross minus k over r squared E sub r, and that's identically 0 because again it's a cross product of r with the radius unit vector in the radial direction, and that's 0 identical. So this implies that L is a constant of the motion. Nowhere have we used that this is an inverse square law really, because this force, as long as this force is a central force, would immediately imply that this is equal to 0, because this force will be proportional to E sub r. Doesn't have to be inverse square law, but it's still true. So this is a crucial point, that angular momentum is conserved about the center of attraction is conserved, center of force is conserved for all central forces, orbital angular momentum is conserved. But now a little piece of magic appears, and that's the following. Consider the vector and let me call it A. This is equal to P cross L minus m times k times the unit vector in the radial direction, so mkr over r. Consider this vector, and it's got a special name. It's called the Laplace Runge length vector, and the claim is it too is a constant of the motion. It too remains unchanged as the particle moves in its orbit. And I am going to give this as an assignment to you, but you can see how this is going to work, because what we need to do, and let me go through a couple of steps, d over dt is the time derivative of this times L. So dp over dt, remember, is the force. So the first term is going to be the force, which is minus k over r cubed r, that is the unit vector, k over r squared times the unit vector here, cross L is r cross p. So that is the first term, and the second term is p cross dl over dt, but dl over dt is 0. We know that L is a constant of the motion. So that portion, this whole derivative of this whole term is just this minus mk, and now you got to be very careful. First you differentiate this r, so it is mk over r, dr over dt, but dr vector over dt is just the momentum p, plus the derivative of this 1 over r, so it is equal to mk over r squared in this fashion, times dr over dt, and then this vector sits there in between. But this is a mess, we do not know what it is. So the trick is to multiply by r and divide by r. It gives you r cubed. There is an r cubed here, you see what is going to happen, and then use the fact that r dr over dt equal to r dot dr over dt. That is a vector identity we proved a little earlier in general for any time dependent vector. So if you wrote it like that, this is r dot dr over dt, but now you combine this m and the dr over dt and write it as r dot p. Here. Now use the identity for the vector triple product here and you're home. This vector has a 0, is identically 0. So this vector is a constant of the motion, and now it remains to figure out where it is, and you can do it, what it looks like, which direction it's in, and that can be done wherever you are on the orbit, any convenient point. For instance, if you're here on the orbit at this point, for instance, the p vector is in this direction, the r vector is in this direction, r cross p, the angular momentum, goes in, and then you got to do a p cross L, whatever has gone in, and the result is going to be a vector which when added to this fellow here is going to give you, so that vector is in this direction, this is going to be p cross L, and this vector minus this is this vector here, that is A. This is ER minus this guy here is minus is mk ER, and we want the negative of that. So you want this plus this, which is this vector here. So it's in the direction along the semi-major axis pointing from the center of attraction towards the shorter end, towards the point of nearest approach of this planet or this orbiting body. And this vector is a constant. I might as well mention that it's related to the eccentricity. Its magnitude is related to the eccentricity of the orbit, and the fact that this vector is a constant of the motion is in some sense responsible for all the magic properties that you have in the case of the Kepler problem. I thought I'd mention this because it's an interesting little exercise to show that in addition to L and the energy itself, you also have this constant of the motion, and a little bit of vector algebra, vector calculus will tell you how this is a constant of the motion and what its physical significance is. As I mentioned, its geometrical interpretation is that it relates directly to the eccentricity of this elliptic orbit.